over in civil environmental engineering, introduce our speaker for today.
All right. Well,
Here's your camera.
oh, all right. Yeah, so I'll keep this brief. So happy to introduce Tony Sebastian. She's an assistant professor at University of North Carolina, Chapel Hill. And originally from Texas, PhD at Rice and things like that. Yeah. And so she does a lot of really cool stuff that overlaps somewhat with what I do on extreme rainfall and flooding, but also a lot of work on coastal flooding, compound hazards, more on human impacts as well, and I think we'll see some of that today. She's also done, she was a Fulbright Fellow at the Delft University of Technology in the Netherlands, one of the top universities in the world when it comes to hydrologic hazards. And let's see, American Society of Civil Engineers Scientific Committee on Climate Adaptation, as well as the Committee on Coastal Engineering Sciences. All sorts of other very impressive things, but I think we'll let her speak for herself. So,
awesome. Thanks, Dan.
Welcome you.
Well, thank you for the introduction, and I'm going to try not to talk anybody's ear off today, but I have a lot of slides, and we'll see where we get. But I wanted to talk a little bit. I traveled all the way inland to the middle of the country to talk about tropical cyclones. So I don't think there are very many people working on tropical cyclones here, but I'm going to talk about them anyways. And I'm going to talk a little bit about the hazards that they create and also sort of the risk and the implications of the risk. And I think there's large-scale lessons that we can draw for all types of flooding events that are happening around the U.S. But really, my research focuses on the drivers of change, and I'm using process-based models, both the physics-based kind, but also some statistically based or like machine learning-driven models to understand how flood hazards and risk are evolving over space and time. My background is in civil and environmental engineering, but I'm now in a earth sciences, broadly environmental sciences department, so I've kind of shifted the way that I think about floods and flood hazards from just trying to, let's say, mitigate their impacts and design solutions for them into more studying them and thinking about this evolutionary process. So just as a little bit of background, I think we all probably know, but we're seeing an increase in the costs of flooding disasters globally, even though we're investing in mitigation. And importantly, a large percentage of global flood losses are uninsured. About 85% of them are uninsured. And I'll talk about why this is important, but I do want to point out that global flood losses are quite large already. So they're about $300 billion US between 2018 and 2022. So these numbers are a little bit outdated, but they're projected to grow exponentially over the next couple of decades. And this uninsurance gap, or what's also known as the protection gap, is likely to widen as insuring disaster losses becomes more risky for insurance providers, right? If we don't really understand where the hazards are or how they're changing, it's going to be harder to offer insurance because we don't know if we can make money on that insurance offering. And it's also going to become more costly for policyholders as insurance providers try to hedge against that risk by making insurance more expensive. And so as sea levels rise, as the climate changes and drives different types or increasing frequency of storms, we're expecting that the protection gap is going to widen. And this is important because this underinsurance or this protection gap, when flood events happen and cause damages, that can have really cascading social and economic consequences for households, businesses, and communities. So we've been seeing these headlines around climate change potentially sparking the next home mortgage crisis, or businesses losing lots of dollars as a result of flooding, or potentially climate change beginning to bankrupt some of America's smaller, especially rural towns. And so my research focuses on all of these together. But I would argue that addressing these types of, we'll call them systemic risks to households, businesses, and communities requires a much better understanding of floods, where they occur and their historical prevalence, and also how they're accruing, how the risks of these flood events are accruing over time than we have right now. And so why don't we really understand where floods are happening or how they accrue over time? Partially, this is computational limitations. So historically, The cost of modeling flooding at the scale of their impacts has been really, really high. So we've just not had the models that can really do this well, or the computational toolboxes that we need to model flooding. Many of the models historically are designed to simulate one of the flood processes, but we know that floods can be driven by everything from rainfall to storm surge to combinations thereof. And also, we have very few observations of historical flooding, and we have very little data on the impacts when these historical floods have occurred. Unfortunately, the intersection of these computational limitations and data limitations are where the most interesting problems are. And I would argue that the playing field is shifting rapidly right now. So reduced physics models are allowing us to simulate more and more of these hazards. Machine learning and AI are opening new approaches, whether that's based on remote sensing data or observational data sets that are out there to simulate past floods. We also have high performance computing, or advances in high performance computing, that's allowing us to do more computation than we used to. There are new hazard event sets being developed all of the time. Big data on exposure, so we're seeing both, I would say, on exposure and on some of the outcomes or the impacts of flood events, different ways of collecting data or different ways of accessing data that we didn't have before. So things like cell phone locations or travel times to places. There are just these huge data sets that are becoming available that provide more insights into how floods are impacting people. And so many of the projects in my lab boil down to where has it flooded in the past and where could it flood in the future. As I sort of argued so far, where it's flooded in the past, we just really don't know much about where past floods have happened, both spatially and temporally. And where it could flood in the future provides a lot of information on how we could plan, design, or adapt to those future flood events. And more specifically, I work, and I have to do this because I'm in an earth science department now, I work on human or policy timescales, so I think about the recent past and maybe the distant future. And when I say recent and distant, I'm talking about 100-year timescales, so not millions of years. But I ask questions like, how did past development and mitigation decisions get us to where we are today? What decisions are being made in the short term, like immediately after a disaster, that are influencing long-term disaster outcomes? And what does the future hold, or what opportunities are there to adapt to these changing hazards? And I use a combination of data-driven approaches and physics-based models to answer these questions. So leveraging all of that newly available data and toolboxes. And in the interest of time, I'm only going to talk about, let's say, 2 lines of inquiry. It's a little more than 2 papers or 2 projects, but 2 lines of inquiry that are currently ongoing in my lab. One which is focusing on simulating tropical cyclone flood hazards in a changing climate using physics-based methods, and another one in which we're trying to characterize recent flood losses and simulate their financial impacts in a more data-driven framework. So in the context of tropical cyclones, why do we study tropical cyclones in North Carolina? Well, first of all, we get a lot of them. This is a map of all of the tracks of tropical cyclones since 1857. There have been a little over 63 of them that have actually crossed the state of North Carolina, but many, many tropical cyclones that make landfall or don't make landfall or make landfall further inland also drop rain over North Carolina. So we see more than just these 63, but on average we're talking about like 2 or 3 tropical cyclones crossing the state somewhere per season. And for those of you who haven't thought about tropical cyclones in a while or need a quick refresher, these are large systems that form over the ocean in the mid-tropics. They travel in the mid-latitudes. They travel towards the land, gathering all of this heat potential from the ocean surface. They begin to spin because of a combination of convection processes and the Earth's motion. And as they progress towards the land, they can generate wind-driven storm surge, but once they cross onto land, they also drop immense amounts of rainfall. And relative to other parts of the United States, North Carolina receives a pretty large fraction of its annual precipitation from tropical cyclones. So about a little over 10% of the extreme events that have happened in North Carolina are tropical cyclones. And this accounts for about 20 to 30% of all precipitation in the state of North Carolina. Past floods have had really devastating impacts both locally and regionally, so we get floods everywhere from the coast to the mountains. I used to say this and it was a big surprise, but I think everybody knows something about Hurricane Helene now. And so we see flooding all over the state as a result of tropical cyclones. These are just some of the really notable examples from the past 20, 30 years. And the majority of historical flood exposure in North Carolina or in eastern North Carolina can be attributed to tropical cyclones. I pulled this data out of a paper we recently wrote. We only focused on the eastern half of the state, but I would argue that if we looked over the whole state, this probably holds fairly true. About 90%, a little over 90% of flooded buildings in eastern North Carolina over the 25-year period in the study can be attributed to tropical cyclone-related flooding. Again, there's been lots of modeling of tropical cyclone storm surge, but tropical cyclones drop this immense amount of rainfall, and especially for the state of North Carolina, that's a really big deal. Future tropical cyclones are expected to be wetter and more extreme. So if I were to summarize a couple of key IPCC style assumptions about how tropical cyclones are going to change, they're very likely to drop more rainfall than they drop now with more atmospheric moisture holding capacity and higher temperatures. They might be shifting further northward because oceans are warming. The jury is out on how their frequency will change. There's some evidence that they might decrease in frequency, but when we see them, they'll be more intense. There's other studies that suggest that maybe we've seen a lull in tropical cyclones, so we might see more in the future. I'd say we don't really know how the frequency of these storms is changing, but they're definitely going to be more intense when they occur. And so in my group, we were really interested in how these, let's say, large-scale climate changes might drive an increase in flood hazard and flood exposure in North Carolina and South Carolina. And so we've been using a model called Sphinx, which is the super fast inundation of coastal systems model. It's been developed at Deltaris in the Netherlands, and it's a 2D raster-based flood inundation model. And for people who aren't flood modelers in the room, basically it allows us to drop precipitation onto a grid and then simulate the flooding that is generated over the landscape, both due to the immediate impacts of that precipitation and the precipitation being routed downstream. Uniquely, it can also take into consideration coastal forcing, so storm surge can be taken into the model as a boundary condition, and then the combined impacts of that inland flooding and the storm surge can be simulated, and we can also apply wind on top of the model. So we're getting precipitation, wind, and coastal flooding all together in one model, which is fairly unique and something quite new in the field, especially at this scale. The other piece of this is because it's a reduced physics model, it runs fairly fast. You can run it on a desktop computer at this scale, but we can also set it up in a high performance computing environment and simulate lots and lots and lots of realizations of flooding. And so a student in my lab who recently graduated and is about to go start working at FM Global spent her PhD building a model for Eastern North and South Carolina and validating it and then doing these simulation runs. As I mentioned, a very unique characteristic of Sphinx is its ability to capture these compound processes well. And these are processes that most models don't capture. If you remember from the beginning, I said that many of the models we've historically used to simulate flooding focus on one or another driver, but not the combination thereof. And so because Sphinx can simulate compound flooding, we can also do fun things like try to attribute flooding to different drivers. So we can turn on and off these different processes in the model, such as precipitation, discharge, tides, wind, etc., and try to understand which atmospheric variable is driving flooding on the ground, or which one is dominating the flood response that we're seeing in the model. And so this is just an example of this for the Hurricane Florence simulation, where the darker colors are the compound flooding areas, and the lighter colors are driven by just one of those processes. So inland is purple, those are rainfall-driven processes, and this lighter orange is surge-driven or wind-driven flooding, where the darker areas are, where they're interacting and generating higher water levels. And just sort of for a note, when we try to attribute the compound flooding, we set some sort of threshold where we say, like, above this difference, we're going to start calling it compound. And so we've been using this model to ask questions like, what's the spatial extent of TC flooding in eastern North Carolina? What are the relative drivers of flooding across the coastal plain? How are the interactions between these different flood mechanisms changing as a function of the large-scale climate processes, and what are the future implications for flood exposure and flood risk, or exposure as a proxy for flood risk? And then where do compound floods matter and to whom? This is particularly important, and I'll get to it later, but we don't currently regulate this type of flooding, right? So we think about river flooding, or we think about storm surge-based flooding, and we have sort of engineering standards to which we design, but when they combine, this is sort of unregulated or unknown, unseen flooding for us. And then how might these flood hazards and exposure to these compound floods change in the future? I'm going to talk about one case or one paper where we've done these simulations, but there's actually a couple different studies where we've looked at this. So in one of our papers, we recently completed, it's actually in press, we've been simulating tropical cyclone hazards associated with the SSP 585 high emission scenario. We're leveraging a large Atlantic Basin tropical cyclone data set that has information on storm track, the minimum pressure along the storm track, and we've applied rainfall and wind fields to that storm track to generate sort of synthetical tropical cyclones, both in a historic climate and in a future climate. For the future climate, we're using one ensemble member from CNIP 6, and we chose this ensemble member because it produced the best combinations of rainfall and surge for our region. And again, costs a lot to run many ensemble members, so for now we've only run this one ensemble member. And what it ends up being is about 1,300 tropical cyclone tracks for a historic period that represents NCEP, and about 1,500 tropical cyclone tracks for a future period from the Canadian Earth System model. Importantly, and what I'll point out is, like, that doesn't sound like very many, but since we turn on and off all of the drivers, you have to multiply these numbers by 3, because we do a lot more than just like simulate each of them one time. So several months of simulations in the end. And just to say something about what we were seeing sort of in the, I don't want to call it the raw data, but in the storm data sets, if we looked at what was coming out of our track models for the historic climate and the future climate, we saw that the storms on average had sort of an increase in rain rate and rainfall totals. We also saw a slight decrease in average wind speed. The peak wind speeds remained almost the same between the historic and the future climate data sets, but the average peak wind speeds decreased. And as a result, our storm tides or our storm surge coupled with tides also decreased slightly in that future climate. And so when we simulate all of these storms, we're able to quantify some sort of return period flooding. We did this across multiple return periods, but here I'm just plotting the 1% hazard or the 100-year floodplain, because that's the one we typically think about when we're talking about policy or regulation. And we see a fairly significant increase in flood depth and a bit of an increase in the area or the extent of flooding. Importantly, in these simulations, we didn't consider sea level rise, but I'll comment on that in a little while. So this is just the change as a function of the changing storm climatology. If we overlay this with existing building locations, what we end up seeing is that we have almost a doubling of the number of buildings that would be exposed to the 100-year tropical cyclone flood in a future climate. So it's quite a significant increase. We didn't increase the number of buildings in the landscape, we didn't change the land cover, so you could kind of think of this as a potential underestimate of future exposure, but then again, we also didn't consider any mitigation. So maybe we would develop smarter in the future, who knows. And then we tried to isolate the relative drivers and their contribution to this future exposure. Interestingly, what we end up seeing is that compound flooding is especially important for future flood exposure. In the past, most of the flood exposure was driven by coastal processes, so these storm surge or these wind-driven coastal processes. And in the future, compound flooding becomes a larger portion of the fraction of buildings that are flooded. This is likely due to that increase, or well, it is due to the increase in the rainfall rates that we see from these tropical cyclones. And what I think is important about this is that, again, this is sort of the unregulated flooding that we have right now, because our current models think about the runoff portions and the coastal portions of the flood portfolio. But what about sea level rise? So again, we simulated all of this to look at storm climatology, but we didn't really incorporate sea level rise into these runs. One of the things that we did to just sort of look at what sea level rise might be doing to these distributions is that we took, I think, 100 or 80 or 100 of the largest storms in our data set, and we stochastically sampled potential sea level rises from the future sea level rise distribution to try to look at where do we think sea level rise will have an influence on the future flood, and how much of that influence would drive the compound flood processes. And just kind of to summarize, what we're seeing is that the zone of influence of the compound flooding goes almost 100 kilometers inland, so it's actually a lot larger than I think we previously expected. And as would be expected, some of these areas further inland will be more likely to be compounded in sea level rise. So as your sea level rise increases, your zone of influence of that compound flooding will extend further inland. But we're also going to see a turnover in some of these surge-dominated areas to be just completely water under sea level rise. And so that coastal zone will also sort of increase into the future. And so just some key takeaways from some of this work on future tropical cyclones. Jury's out on how frequency is changing. In our simulations, we didn't change the frequency. So even though we're not changing the frequency of these storms, and in fact, not significant changes to their wind speeds, we do see an increase in flooding as a result of that change in rainfall. And that increase, especially for exposure, is fairly dramatic. Places that are already flood prone will definitely flood more often for a given magnitude or severity, for a given flood probability. Many more buildings will be exposed to future flooding. So for the 100-year flood, we estimate that the number of existing buildings at risk will almost double, and the nature of this flooding will change. So we're expecting that these compound and coastal flood processes are going to account for a larger portion of future flood exposure than in the past. Again, I said this is like one study from a series of studies we've been doing around this topic. We've also done this using a pseudo-global warming approach for a couple of historical storms that were significant in the region. That work's published in a paper by Lauren Grimley in 2024, and we found kind of similar results to these, or these results sort of hold for the PGW storms. The reason that I think the PGW storms are relevant is that they maintain the spatial structure of these hurricanes in a warmer climate that might be, let's say, oversimplified in our statistical dynamical approach that we used here. And then the other piece of this is, projected development patterns might lead to slightly different conclusions. And so there's a student who's also working on that right now to try to couple in some land use change and some development change. So shifting gears a little bit, while I think that these hydrodynamic studies are really important and they're fun to do, and they do offer a much better understanding of how hazards might be shifting in space and time, they don't really give us a good understanding of the impact of these events. They help us project risk, but if we really want to understand the human or the financial impact of these flood events, we really have to look to the past to build our models. This is just like a simple explanation of sort of the recovery cycle, or the way that we think about the recovery cycle. You might have two buildings and they're both exposed to a flood. That flood has some amount of impact on them. They're both damaged, but their recovery trajectories might look different depending on pre-existing inequalities. So maybe this household was uninsured and therefore had a harder time recovering from the flood. Maybe this household was less financially well off and so it didn't have access to capital after the flood event. Many studies have sort of looked at these recovery dynamics, but most of the literature tends to look at it for just one event. And what we've been trying to do is look at the recovery dynamics or these impact dynamics over time across multiple flood events. And in order to do that, so maybe I'll just make my point here, that there are just very few records of past floods. And the ones that are out there vary in terms of their spatial and temporal resolution. So you might have some records that are based on hydrodynamic modeling, so similar to what I showed already. We simulated, I don't know, maybe 3 or 4 past hurricane events at a fairly large scale, and that in itself is unique. And it gives you great information about sort of the hazards that come along with floods, so depth, velocity, timing, they're fairly high resolution. But you need a lot of data to build them, and they're time consuming to run. And so there just aren't very many of these out there, and they tend to be pretty bespoke or for the largest events in the record. There are also these remote sensing data sets, like the ones that Beth and John developed. And they're great because they give you these large scale observations of flooding. And they're getting more data all the time, but they have flyover issues. And in urban areas, we can talk about why, when, and why they fail. And also sometimes there's clouds in the way of the optical sensors. And then finally, there are examples of county level databases of observed losses from flood events. But these, and they're great because they're easily accessible and they're out there, but they're low resolution and sometimes there are reporting biases and inconsistencies. And so one of the things that we recently did in my group was we tried to reconstruct a super high resolution, both in space and time, data set of flood events that have occurred in the state of North Carolina from 1996 to 2020. And as I mentioned, I think you've already kind of seen the results of this in an earlier slide, but what we were doing here was that we took personal level or address level information on past insured losses and policies to build a machine learning method or model to predict where it flooded out of sample. And so we're able to predict flooding at properties that did not have a policy or a claim as well. So that's really important to point out. So using the claims data set, we identified 78 events in the past record. We validated, I'll put that in air quotes, that against other data sets that were out there. So we found 78 events. If you look at presidential disaster declarations, there have been about 18 of them. We overlap with all of those. We also went out and tried to find all the other sources of modeled flood extents that are out there, from remotely sensed imagery to hydrodynamic models. And there were only 6 other events in the data set. And so we're finding somewhere around 60 more events if we look at the historical damage record. And the way that we build these flood maps is that we take the records of flood damage and no damage, so policies without a claim, and we use those to train a machine learning model on geospatial features that you might also use to build a hydrodynamic model. So things like topographic information, such as elevation, height above near drainage, other types of hydrographic features like topographic wetness index, imperviousness, distance to coast, distance to stream, soil hydraulic conductivity, and then some contextual variables that might help us explain why you see more policies in one place than another, like the 100-year floodplain or building density, road density. And for each of the 78 events in our record, we build a random forest model, and we use it to predict where it did or did not flood. And this comes out of the model as a continuous flood probability that we then threshold to generate a flood extent. So we did this 78 times, and what we end up with is a map of where it flooded over these 78 events. And here I've taken this a step further already because it's more interesting to look at it this way. And this is a count of the number of times every building in eastern North Carolina flooded over this record. And so we have some buildings in our data set where we count that they flooded 11 times, but the majority of our buildings in our data set flooded, let's say about half of the buildings in our data flooded just once, and about half of the buildings in our data flooded 2 or more times. I think I said that wrong. Sorry. but have the data where the floodplain, about half were not. About 22% of the data in our, from our flood record flooded 2 or more times, and about less than half of them were insured. From this study, we were able to sort of draw some conclusions about, the frequency of flooding in North Carolina over this record, but also sort of our, this uninsurance gap or the protection gap that exists in North Carolina. So importantly, when we look over this record, because we were able to predict these out-of-sample flood probabilities, we find that about half of the buildings that have flooded over the record never had insurance. And that's significant when we start to think about the potential impacts of flooding on these individuals, but also on the surrounding communities. I'll say something first before I get to the financial impacts, but this data has proved to be incredibly useful for understanding impacts and local community level of responses. It's been taken up in a whole bunch of different studies by colleagues at UNC. Maybe elsewhere, I don't know, we made it publicly available, but these are all people at UNC who are working on a variety of different outcomes related studies and asking questions like, in response to flooding, who has moved and who hasn't? So Helena had this awesome data set on everyone who's ever lived in the state of North Carolina and how long they lived at that location, and so she's looking at how they're responding or how they have responded to flooding at the property level. A couple of people over in the health sciences school are thinking about healthcare access during floods or disruptions in healthcare access after flood events. We have this cool study where we're tracking who's applied for mitigation funds and who's actually received them relative to how often they flooded. Natasha Malman, who's actually at Clemson, she's working on a study looking at school closures and disruptions after flood events. And a couple of students who I co-supervise are thinking about financial risk, particularly systemic risks in the housing market. So to switch gears a little bit and just talk about that work for a second, this is sort of like my other hat, which is more impacts driven and less just flood quantification. So we understand, or we hypothesize, that flood exposure can impact household finances. And this is just a plot of mortgage delinquency rates in southeastern North Carolina, this area that is a fairly diverse area in terms of homeowners. So we have, at the coast, we have lots of high value properties, further inland, lots of low value properties. We have a fair number of mortgage holders across the region. And what we saw was that if you pull this data for the period surrounding Hurricane Florence in September 2018, we see an increase in mortgage delinquency rates after the flood. And there's all these headlines out there right now that are suggesting that climate change might spark the next home mortgage disaster, or that it's bankrupting American small towns. And so we've been trying to create a simulation framework to understand how risky floods really are for individuals, but also their surrounding communities. Because, I think I have this here, you can imagine that if you have a flood event, not only does it cause damage that may or may not be insured, but it also probably has some effect on your property value. And so we sort of hypothesized that there's something about pre-flood property conditions, so your property value, your mortgage holdings, how much equity you have available, what happens during the flood, and how that cascades into some amount of systemic risk. So some amount of risk that is posed to the property owner themselves, who own this property and are dealing with either the recovery or the inability to recover from the flood. And in the case where they can't recover from the flood, some of that risk is then borne by the lenders. And if the lenders walk away from the property, some of that risk might be borne by the local government. And so we've sort of been trying to simulate this cascade of systemic risk that exists in the system. So again, our underlying assumption is that when uninsured damages exceed property values, mortgage defaults and property abandonment become more likely. To do this, and I'm not going to go into too much detail just for time, but to do this, what we've been doing is combining, let's call this environmental, these flood maps that we have with property level data and financial holdings data. So we have information on property values, and we can simulate how those property values are changing in response, or we can observe how the property values are changing in response to flooding. And we can also simulate how people are or are not repaying their mortgage in the wake of flood events. So we have really high resolution, almost property level data on the financial characteristics, and we also have property level data on whether or not a property flooded. And this allows us to simulate balance sheet losses, like how much insured damage and how much uninsured damage there was, what happens to the property value, and how does that interact with people's ability to recover from the flood event, and their likelihood for defaulting or abandoning a property. And in the case of default abandonment, how does that then cascade to the local government who are now responsible for that property in the wake of large-scale abandonment? And so we first did this for Hurricane Florence. So we just looked at one event, and this is now published in Earth's Future. And what we found was there were about $2 billion of loss during Hurricane Florence, and this breaks down into mostly uninsured damage, and then another 50% that can be accounted for in insured damage and also property value losses. So these are declines in property values after the flood event. And when we simulate this whole cascade model, what we find is that most of the risk is borne by property owners, which one would kind of assume, right? Most of us will probably stay and find a way to pay for the recovery, but there is some risk of mortgage default, which cascades to lenders, and there is some risk of lenders walking away from properties because it's not worth investing in rebuilding them, in which case the local government gets saddled with these abandoned properties. What we saw, and I'll show this again in a spatial version, but was that areas with lower pre-flood property values are exposed to these greater financial risks. So in areas where property values are low before a flood, and one might assume, or correlated with that is financial capacity to recover from a flood, those are the places where we see a higher likelihood of this default and or abandonment. So since this 2023 study, we've now looked at this across a couple of flood events. So we specifically pulled out 7 TCs from the historical record. We repeated this, we updated the model a little bit, but we effectively repeated the study. We're using this high resolution flood data and high resolution financial data. And we simulated the amount of uninsured, insured, and repetitive flood loss of these properties. And we tried to interact, so what was happening in between floods played out over the whole timeline. So over this period, we saw about $4 billion in flood damage. 66% of that was uninsured loss, and quite a large fraction, about almost 18% of all of the damage that occurred over this period was at properties that were flooding more than one time, so this repetitive damage scenario. Ultimately, what we found was that about 7,100 mortgages, or 32% of all of the mortgages that were exposed to flooding over this period, were at risk of default. Importantly, not all of them defaulted, right? Like there are mortgage forbearance programs, the federal government steps in with other forms of disaster relief. But if we really played out our simulation framework, we could assume that somewhere around a third of all mortgages could have defaulted during this period. And then I haven't spent a lot of time on this, and just some of my talks really focus on like flooding outside the floodplain, but I do think it's worth noting that about 86% of all of the uninsured damage is outside of the floodplain. And so this has some policy implications around where we think risks are and how we map them and who we try to encourage to buy flood insurance. Similar to the study where we just looked at one event, we're finding that in lower income and economically distressed areas, we're seeing larger systemic risks. So this tends to be this inland, this intercoastal area. So as I mentioned, the sort of the dynamics of the coastal plain in North Carolina are that along the coast we have higher value properties, similar to much of the East Coast. We have these like McMansion beach house scenario. And then further inland we have more rural, but also just like economically less well-off population and lower property value, because this is sort of just our inner coastal plain, and then our big cities are here. And if we look across all of the events, we also see a larger, cumulative uninsured flood damage in these places. Okay. All right. So, just to kind of wrap it up, and I talked faster than I thought I would. So there's ample evidence, I would say nationally and maybe even globally, that flooding is becoming a growing issue for homeowners, businesses, lenders, and local governments. We sort of play this out in North Carolina specifically, but I think this is sort of a trend we're seeing and maybe also in response to other types of climate-driven hazards as well. In North Carolina, this rate of change in exposure is outpacing our attempts to address it through adaptation. So some of the other work we've done, and this is just an example of it, looks at how quickly we are investing in mitigation relative to new development. And we found that in the past 20 years, can't do math in front of a room, 30 years, for every one structure that we bought out of the floodplain, we built 10 new structures in the floodplain. And so, buyouts are hard to do, and we can have a whole conversation around the problems with buyouts, but it's just sort of an example of what's this dynamic that's going on, that we're piling people into these flood-prone areas before we truly understand what the hazards are or how they're changing, and we're also not necessarily regulating the way we develop. In North Carolina, luckily, if you develop in a flood-prone area, you do have to meet a certain elevation standard, et cetera, so I'm not suggesting that every single one of these new houses will flood, but I think that this is just sort of emulates the point. We also have very weak land use policy in North Carolina. So some of my other work and other students that are in my lab are working on these questions around how development changes might drive an increase in the hazard as well. So not just about where we put it, but also how we develop and what that means for the changing hazard and the feedbacks between those development patterns and the hazard. So there's little appetite in North Carolina for smart land use practices. And I think that's probably, I worked in Texas for a long time, it's not just North Carolina. Flooding could present a systemic risk to the financial system, particularly in these intercoastal or low property value regions, and especially if the federal government no longer provides a backstop for financial risk. So I think we haven't really seen this problem play out at scale, in part because we've always had sort of federal government protections, but as that gets pulled back, I think that the riskiness of these TCs and other types of flood events is going to go up. And then finally, I would argue that these systemic risks are particularly difficult to address through policies because we really lack an understanding of where they are and how they're accumulating over time. So one of the things that we're trying to do in North Carolina is help the state government potentially target areas where they might want to subsidize insurance, because you can see in our model that providing or encouraging uptake of insurance or decreasing that protection gap would actually reduce the systemic risk fairly substantially. And so we're not only working with the state government, and you can kind of argue to the state government that they can push some of that risk off to the federal government, so that's a nice red state strategy we're playing out. But we're also working with some insurance and reinsurance companies who are really interested in thinking about community-led parametric products, or let's say small add-ons to your homeowner's insurance policy that would cover the really, let's say, the less than $10,000 or less than $50,000 damages. So could we increase insurance uptake to address some of this problem is something else that we're thinking about a lot. Much of what I said in this presentation was collaborative work, and much of it was led by students. I tried to pull them out on the slides when they were there, but especially Hunter Quintal, Helena Garcia, Kieran Fitzmason, Lauren Grimley, and Hope Thompson worked on parts or all of this presentation. And the work's been funded by North Carolina, the state of North Carolina. They're really interested in understanding sort of current and future TC risks, including NCDOT, NOAA, which was terminated and then restored, and DHS Coastal Resilience Center. So thanks for listening.
All right, thank you. Very much appreciate presentation. We do have some time for questions, if, I'm sure there are some, but.
Yeah.
I have like 45 questions.
I was like, what could I talk about?
Restrict you. I'm gonna
I will
restrict
ask
you.
one. I get to cook Tony dinner later, so I'll say the other 44. Okay, my number one question in this room is, tell me more about the development of land use scenarios. Like, I feel like I parrot this phrase from earlier flood model studies that like, the real driver is development, it's not climate change. And like, climate change is a little bit of a scapegoat of like, what's the real underlying problem? But then you show this compound flood study, like the first half of your presentation, and I'm like, oh, do we just think climate change doesn't matter that much because all of the models that do those analyses look at river rate flooding and storm surge and not the compound element? And is there's this theme about rapid intensification and rainfall and tropical cyclones that challenge this story that I've believed and been telling everyone else?
Yeah. Okay, so here's what I'm gonna try to come up with like the most concise answer because we can talk about this all day. So like my other passion is land use, and Beth knows this. With the PGW runs we've done, that student has actually also used the ICLIS future projections of land cover. So we have actually simulated the land cover change as well, and I haven't really seen that done at this scale. And so what's really interesting, because I've done a lot of work on land use in Houston, and I've done a lot of work on land use in like some of these smaller communities, but what's really interesting at this scale is that land use increases the flood hazard on a fairly short spatial scale. So what we see is that locally, land use is a huge driver of increased flood hazard, but at the regional scale, climate is like the dominant driver. So I don't know if that helps explain it, but, and I wish I didn't throw the map in here, but like for example, in North Carolina, this area is projected to grow because there's military there and stuff. And so what we end up seeing is that like kind of to here, there's an increase in hazard along the river, but then it like doesn't, it dissipates. That impact dissipates as you move further downstream. And so the storyline that we're trying to play out for that paper is something about local to regional changes and what matters. So in terms of maybe putting a different lens on it, if you think about policy, land use policy really matters at the city scale because that is where we're seeing the land use influence play out on the hazards. But at the regional scale, it's climate that's driving the hazards like for the state of North Carolina. And so there's kind of this like different policy making levels that comes into play when thinking about land use. So I don't know if that totally answers your question. I think it's really a question of like at what scale are you looking? So at a city scale, land use does matter and it sometimes matters more than climate.
Yeah.
But at this scale.
But my question, so you're saying like land use matters in terms of amplifying the hazard, but my question is maybe more about exposure.
Yeah.
Like, is exposure growing more? Like, if we think about building cats flooding,
Yeah.
is it growing more because TCs are dumping more rain on North Carolina? Or like you mentioned this other word of future land use, or is the exposure growing more because people are building in places where that will occur?
I don't know the answer because I think that probably depends on the dynamics of that change. Locally in North Carolina, a lot of the new development is going in like here, right? Like this is Wilmington, it's growing. This is also growing. So I do expect that where the new buildings will go matters. But it's also a question of like how are the new buildings built? Right? So if they're all elevated and they have tie-down roofs, is how much more risky is it getting? Those dynamics I'm really interested in playing out, but I don't have a good answer for you. But yeah.
Other questions?
This is fascinating. I've got multiple questions too, but I'll try to just ask one. So I'm interested in kind of the rural county aspect of this too, and thinking about their budgets and their costs following these disasters.
Yeah.
And I know you're focused primarily on just property damage, but what about like damage to public infrastructure, roads? I mean, that, in my experience, seems to be really tough for county governments to handle after a disaster. Is there a way to kind of include that in this analysis or put it in the context of?
Yeah, so exposure is fun to play out on buildings because it's fairly straightforward. You're like, is it gonna flood or not? What I hear from DOT in the state of North Carolina is duration is really important for road damage. And so we've been trying to start storing our duration output, but also validating the duration output. Like I have questions about how good our duration output really is for those types of analyses. So just like on the road side. But you are right that the public infrastructure component of this is really important. And actually a lot of where the recovery dollars that the state gets from HUD go towards are those public infrastructure projects, and especially in rural communities. They really need those state dollars because they don't have the tax base themselves. And I think also in the systemic risk conversation, that's a lot of where you could start to see these like community level systemic risks play out, where it's not just decline in property value, but also decline in services. I don't know if this is a good answer, but I would say post-lien in North Carolina, the lack or the slowdown in the pace that the federal government came to the table was a big concern. And North Carolina is fairly well prepared for these storms. Like we are fourth in the nation in terms of number of tropical cyclone landfalls. Like we know they're coming. We have a pretty big budget to deal with it. We've got full-time staff at the state level who respond. Other states don't have that. And so like as the federal-state relationship in disaster response is starting to break down, I think that is going to be a problem we talk a lot more about. So I don't know if that's a good answer, but it is something that is, that I'm hearing more and more of concerns about that. And in Western North Carolina, like telephone pole, like the electricity situation is still pretty dire. Like everything's just kind of strung up on side of the road poles. Nothing's really back in place yet, and so it is still like a very much an ongoing conversation. It's not covered at all.
Any questions?
Awesome talk. I also have a lot of questions, but like everyone else, I'll just treat it as one. You were talking about compound flooding being unregulated. I was wondering if you could make that connection a little more.
Yeah, and that's sort of this term that I've applied to it. So what I mean by that is that the regulatory floodplain maps, and I usually have like a set of slides, and I don't want to subject everybody to my 100-year floodplain concerns, but the regulatory floodplain maps represent the hazard associated with either riverine flooding or coastal flooding. Exactly what they do in the coastal zone, I can never quite get a straight answer on, but I think it's the max of either. And so if you imagine that the actual physical interaction between those two processes could elevate the water level beyond either of them, that is the piece of the puzzle that's not considered. I would also say those two processes are simulated using totally different methods right now. And so it's not even like the same flood that creates the coastal hazard is the flood that creates the river hazard. So it's not just that they're not simulating the dynamics, but actually it's just like two different processes used to model those things. So we're just missing the dynamic interaction piece
You're
of
saying
it.
like the processes that build the regulation are not considered as compound flooding,
Yeah.
therefore likely this represents a lot of places where people are.
Yeah,
sure.
and I'm not saying that these, so for example, these pink dots, I'm not saying that those aren't places that would be subject to one or the other. It's just that the total water level in these places is higher because there are actually dynamic processes at play that aren't modeled in the regulatory framework. What I haven't done and what I really want to do is overlay our maps with the 100-year floodplain. It's something that's in the back of my mind to do, but it's more of a curiosity question than a science question. So I've been calling that unregulated. But really, if you think about it from like a building level standpoint, right? If we are setting standards for the bottom floor elevation of building or the first floor elevation of a building based on the river or the coastal, but actually that level should be a little bit higher. That's kind of that unregulated piece that I'm talking about, is like the building regulations in those places. Yeah.
Maybe one more?
Yeah, so that is probably worth pointing out here, is that like these numbers are exposed buildings because we don't have a lot of detail on exactly, we didn't take the step to like whether the building would collapse or how much damage would occur at this building. This is just a count of buildings that are located in areas that would flood. So it's totally possible that a fraction of these buildings, especially the ones at the coast, are elevated high enough outside of the 1% hazard. I didn't want to get into all of the uncertainties around buildings, so we haven't taken this to the step of risk yet, because that's a whole nother beast. So right now we're just kind of playing out building counts.
Okay, one more question.
Very, very kind of a big question about, so you mentioned about the regulatory floodplain map. Are they done by the same agency or done by different agencies? Because there's definitely some more on the ground of flood, but also coastal flooding. To
Yeah.
me, it seems to me there are two different, if I understand correctly, measuring the area. How do two different agencies?
So the floodplain maps are all done by engineering firms, but there's a different process for modeling the coastal floodplains, and they were actually done in one fell swoop for most of, there are like segments of the coast where they ran the simulations all at once. The inland floodplains is a much more complicated process where they're really mapped on a very, very local scale and then stitched together. So they're not all the same age, they're not all done by the same engineering firm. They're updated on different frequencies. So I don't know if that really answers your question. The policies are set by different agencies, but the actual mapping is done by engineering firms, and it's a very ad hoc, might be the wrong word, but
But you are doing by yourself
yeah, this is just one framework for everything.
with coastal flooding as well as
Yeah, coastal.
the inland flooding.
Yeah. Yeah. So maybe I overlooked that statement, but we loosely couple the ADCIRC model, which is the standard coastal model for coastal floodplains, together with the Sphinx model. So we drive it with that model.
Great, let's thank Tony for